Hi, this is the next video in the series of correlation and regression videos that examine relationships amongst variables. We have so far examined what correlation is and examined the concept of regression. Now we're going to move into actually conducting simple regression using our territory sales data. Here we are into simple regression. Simple regression is simple. It is simple because it only has one predictor or independent variable. This is the general form of simple regression. You have y as your dependent variable and x1 as your independent variable. There is only one independent variable, making it simple regression. B0 and B1 are parameters that are estimated using ordinary least squares method that was discussed in the previous video. So let's get to work here. Let's actually put this knowledge to practice. Let's see if we can examine the relationship between advertising and sales. Did I say relationship? I must have meant influence or effect. The distinction is subtle but important. When one talks about a relationship, one isn't specifying what affects what. Here, our question is, does advertising influence sales, which is indicating the existence of directionality in the relationship. Advertising is being hypothesized to affect sales or cause sales. I know cause is a strong word, and to reinforce the point made in the previous video, one cannot know for sure that X is causing Y unless one has really strong, solid theory and an experiment to back it up. Yet, we do make such assertions when conducting regression. We assume that the theory is solid or an experiment has been conducted in the past to support the existence of a causal relationship. So going forward, I'll use the term cause and an influence to indicate directionality in a relationship. Anytime you see the word cause or influence or drive or effects, you should also assume directionality in the relationship. On the other hand, if the term is merely about relationships, well, then directionality is not assumed there. So our goal here is to examine if advertising influences sales. Specifically, we're looking to see here if, to examine the hypothesis, let me scroll up to grab that bit of script. So here is what I wrote before for the general form of the overall regression hypothesis. Just pasting that in here, we're going to paste that and adapt that. So predictors do not influence the outcome variable, which here is what predictors is. We only have one of them, right? That's advertising. So we'll just, fix the vocabulary here. Advertising does not influence sales. And H1 is advertising influences sales. That is your H1. Let's go on now and examine this relationship using regression. We'll test this hypothesis out and move on. So to do so, we're going to follow these steps in Spss, specifically these one. Okay. Before we go on, let me just do one more thing here. We also have variable hypotheses to specify out here. Let me again state what those would be. Advertising does not influence sales. Advertising influences sales. Oops, did I make a mistake? Isn't that what I wrote in the previous slide? I did. Well, it turns out when you're examining simple regression, this is not a mistake. There is only one predictor or independent variable. The hypothesis here on this previous slide examines the effect of all the predictors together on sales, but we only have one predictor, advertising. So whether you're looking at all the predictors together jointly or individuals, each variable, it's the same thing. So in a sense, then the result of this hypothesis is going to be the same as this one. We'll see that very soon in the results when we run the regression. So we're going to do the following in Spss. Let me head over there next. So off we go to Spss. Here's our data. We've got sales, advertising, represent, WEI here. I will go analyze, regression, linear, where I'm going to move sales into dependent space and advertising to independence. That's it. Okay. Oh, before we move on, pay close attention to the terminology here. We're no longer talking about relationships, so the variables are explicitly noted as being dependent and independent. More generally, dependent is also an outcome variable, and independent is seen as a predictor variable. Okay, let's examine our results and interpret them. Here's the result of running a simple regression. You're going to note right away your R squared is 0.775. See, let me go back up a second here. Let's go to our first table, examine that first. So the very first table tells us what is our independent variable and what is our dependent variable. It talks about a method called enter. We'll talk more about this later. For right now, just take that as a given. That's the default method used in SPSS. We'll modify that in a later session. On running this model, we obtain an R squared of 0.775. This R squared of 0.775 turns out has a corresponding F statistic of 130.644 and a p-value of less than 0.05. So you have here the R squared measures in model summary and the statistical test of the R squared measure in the ANOVA table. In other words, what's being tested, what is being noted out here is being tested in the next table below. They're sort of related. A case where you might want maybe these to be in one table, and an argument can be made of why they should be in one table. So let's go and put these into our slide so we can connect the dots. Okay, so our R squared is, or turns out to be, 0.775. And the corresponding F statistic happened to be 130.644. And the corresponding p-value was definitely less than 0.05. So the conclusion is that the predictors jointly influence, outcome variable, right? Outcome variable is sales, so we'll replace that as sales. Given that we only have one predictor here, let me just go ahead and directly say out here, advertising influences sales. Now, some people would say that, in a sense, what the hypothesis above is testing is whether R squared is equal to 0 or not. So R squared cannot be 0. You're testing to see if it's more than 0. And that would be an accurate characterization. That's R squared. Okay. Let's move on then and examine the second part of our output, which is what is being asked of us in this next slide. Second part of our output shows us the coefficients table. The coefficients table tells us that for the only variable in our model, advertising, the unstandardized regression coefficient is 25.308. Has a standard error of 2.214. 25.308 divided by 2.214 gives us a t statistic of 11.430 and a corresponding p-value that's less than 0.05. In other words, all this tells us the following. It tells us that our t statistic is 11.43, and the corresponding p-value is less than 0.05. So here again, it's safe to reject the null hypothesis here. Our p is less than 0.05. We can reject the null hypothesis that says advertising does not influence sales. In other words, we're saying advertising does influence sales. The same thing we said in the previous slide as well, but bear in mind, that is the nature of simple regression. Your overall hypothesis is going to give you the same inference as the variable hypothesis will. A regression equation looks as follows. We have a general form y equal to beta 0 plus beta 1, x, beta 0 plus beta 1 x1. In this case, y is sales, so sales is equal to, it's a function of our variables. Let's go and take a look at them. So our variables from the coefficients table are right here. Sales is equal to 135.434 plus 25.308 times advertising plus error. Put that in the equation then in our slide. Sales is nothing but 135.434 plus 25.308 times advertising. Okay, plus some error more. Okay, so let's take the error out for right now because we are predicting estimated sales or going with estimated sales. When you're doing estimated sales, you can drop the error term. Sales is the constant 135 plus 25.308 times advertising. This is a powerful equation. This equation can allow us or enable us to estimate what sales would be given a certain level of advertising. Take, for instance, if somebody said, well, what would be the expected sales for 3 TV spots? Well, the answer is 135 point whatever plus 25.308 times 3, whatever that comes to be. Similarly, if somebody wants to know how much would it be for 4 spots per month, well, that number is going to be times 4. Now that's great. We know how much 3 spots cost, 4 spots cost, some number. What's important here, somebody might want to know that, okay, so it's good to know 3 spots is going to make me so-and-so sales on average for a territory. And so 4 would generate so much sales. But what if I have a certain level of advertising already doing, and if I add 1 more TV spot per month, how much will my marginal increase be in sales? Well, that number is going to be, well, you can do the math out here. 135.434 plus 25.308 times 4 minus 135.434 plus 25.38 times 3. Or I can just tell you that is exactly the meaning of the regression coefficient B1 or beta 1. In other words, the additional sales will be 25.308 units. So how much more sales will 1 TV spot give us? 25.308 units of sales. Wow, that's awkward. 25.308 units of sales. That doesn't mean a lot. What is units? What are the units of sales? Let's figure it out. Let's go over to our Spss data set. Okay, sales is, units of sales is thousands of dollars. Right, so 1 more TV spot will give us 25.308 times 1,000 or $. I'm just going to keep this as units, which is same as saying $2.5 to 308. Okay. So 1 more TV spot per month will earn them another $25,000 in sales for the territory. This can enable a sales manager to make the call, make the decision, is it worth their while to spend more money on TV advertising or not? Okay, let's move along now and repeat this process for another example. we will now look at the effect of sales reps on sales. Specifically, does number of sales reps influence sales? So here a null hypothesis before is going to be, well, predictors, do not influence sales. Put them all together, outcome variable. So that's a generic kind of term, which is basically saying, same as saying R squared is equal to 0, or not significantly different from 0. That's what it basically means. And so that's basically what we're saying. Okay. And then H1 is saying that predictors do influence outcome variable, and that's being R squared is not equal to 0. So that turns out to, or greater than 0, because remember, square can only be positive. So a way to simplify this is say here predictors in our case is sales reps, or number of sales reps, and then our outcome variable is sales. So we'll simplify this one also. Predictors are, it's only one number of reps. And oops. That's it. And then we can go and measure, figure out R squared from this, or F statistic, p-value, and so on, draw a conclusion from this whole thing. So let's go ahead and well, before we go, let's go on, plug in some more hypotheses here. So our variable hypotheses are going to be identical to what we had for overall, that is number of sales reps. Non-influence sales. Great. And just so you know, what we're testing out here, essentially, we're seeing if the coefficient of sales reps is 0 or not 0. Beta 1 or the sample statistic B. So we're seeing if this is not equal to something precise. Great. Okay, so we have this all set up. Now let's go ahead and run the analysis to see what we find. So I'm going to go into SPSS now and run this for us. So we have factory territory sales data. We'll look at analyze, regression, linear. We're going to examine a relationship again. I'll reset this view. So we are looking only at what we had, well, a clean slate. Sales is dependent variable, and number of sales reps is our independent variable, or our predictor variable. So excuse me, just analyze this one more time. Analyze, regression, linear. I wasn't feeling good about that one, so let's do it again. Sales goes to dependent variable, and sales reps goes to independence variables. And now we can hit OK on this. And we'll get our output in the output window, which looks as follows. So our starting table is same as last time. We have here number of sales reps showing up as variables entered, and we're using the enter method. Dependent variable sales in thousands of dollars. We have an R squared of 0.778, pretty large R squared, I must say, and I'll comment on that in just a minute. Our first question is the R squared equal to 0, or is it, greater than 0? And to test for this, we are going to look at the F statistic and the corresponding p-value. Numbers are right here. Okay, so what are these numbers? Let's put them all in context. So we're finding out here our p-value is less than 0.05, telling us then that the R squared is in fact more than 0. We can then reject our initial hypothesis in this. We can then reject this null hypothesis and conclude that R squared is significantly greater than 0, because when we looked at our table, our R squared was 0.778. and the F statistic of 132, and a p-value less than 0.5. Okay. So conclusion, sales reps, number of sales reps the last example I didn't comment on the size of the R squared, right? A strong effect, right? Based on the size of the R square, I could say this is a strong effect, okay? Because the R squared is more than 0.5 threshold for a strong effect. We can then move on to examine the individual variable hypotheses. So look as follows. So again, we'll go back to our output window and fish out our coefficients table. And from that, we'll find out the value of the number of sales reps regression coefficient. So the regression coefficient for number of sales reps is 6.244, standard error 5.748. 66.244 divided by 5.748 is 11.524. And that gives you a p-value that's less than 0.05. Putting all these facts together in our slide, we'll bounce back over to slide here. Our t-statistic appears to be 11.524. So t is 11.524, and our p-value is less than 0.5. This leaves the regression equation that is as before, sales equal to a constant. Let's see where we get the constant from again. Go back to Spss so I can highlight where we're getting these numbers from. We're going to pull out the numbers here from this table where we're going to look for the constant regression coefficient of the constant and the unstandardized regression coefficient for number of sales reps. These are 80.066 and 66.244 plus 66.244 times reps, right? Those are our numbers for our regression equation. So your expected sales or estimated sales for a territory with 2 sales reps would be, based on the equation, simply take these numbers and plug in 2 for reps and get essentially. This would be estimated sales. And let's just because I didn't do it last time, let me just complete this one out. So here are the numbers. Let me just, oops. Let me just finish doing the math on this one. You do that math, you're going to get, oops. You get 212.554. Oops. Which is same as saying $212,544. Okay. Now, in the same vein as the last time, we now have what is the impact of adding 2 more sales reps on territory sales? We already know the interpretation of the regression coefficient 66.244. What it means is that when reps goes up by 1 unit, sales goes up by 66.244 units. So if reps goes up by 2 units, sales will go up by 2 times 66.244 equal to whatever that is. Let's do that. That is going to work out to 132.488, 2.488 equal to $132,488. In fact, so then we're telling the boss, well, if you add 2 more sales reps to territory, we're going to boost, our sales by $132,488. Now it is for you to decide, is it worth your while to hire 2 more sales reps or not? Is the marginal impact, justify going with that hiring decision? Okay. In this section, we've looked at examining sales reps independent variables one at a time. This is called simple regression. Well, simple regression is simple. It is not used often because the view is that we live in a complicated world where many variables coexist at the same time. So examining just a narrow cross section of the world is impractical, and therefore multiple regression is what is most commonly used. That is going to be our next topic that we'll look at in the next video.